All right, I am just waiting as people log on to the website before we start. So this is Math 175, Lesson 1. Today. And this will be a pre-calculus review, a little bit of calculus, a little bit of trig, and calculus proper starts on Monday with the study of limits. So what I hope you can see is this nice white piece of paper that says Math 175, Lesson 1.
We can see it.
Good. So, okay, so let's start slowly because it's the first class and some people might have a little bit of trouble figuring out how Zoom works. Every one of these lessons will be recorded and I will upload the video to the channel on YouTube. So you can go to YouTube and there is a channel called Nathanson Math Lectures, and there are various playlists, and one playlist will be the lectures for Math 175. So usually within an hour or so of finishing class, or a couple of hours, because I have a class right after this, I will upload the video. So if you missed the lecture or if you want to see parts of it again, you can go to YouTube and it will be there. So I should have posted, well, I have posted the syllabus for the course. It's the departmental syllabus. So this is the syllabus that is always used for Math 175. This semester, there are actually two variations because some people are choosing to use the syllabus that is tied to the textbook. Other people are choosing to use the same syllabus, but on a website that includes something like a calculus textbook and problems. But since we hope that this online system won't be lasting for very long, it's better to follow the standard model for the course, because if we're back on campus in the spring, we'll be following the standard model for Calculus 2 using the textbook. There are 28 classes in a semester, and each lesson is spelled out in detail for on the syllabus, in particular the homework problems that are required for each lesson. There are a very large number of homework problems, and it's sometimes hard to do all of them, but you should always do some. And if you're going to do some but not all, try and make sure you do a selection of problems on different topics. If you always do like the first 10 problems of the homework assignment, you'll be covering probably one topic in depth and not doing anything else. The exams will be given online. Probably if this is not your first semester at Lehman, you've already done this in the spring or in the summer school, so you know what the technical complications are, but we don't have to really worry about that until we get to close to the first exam. The syllabus problems are based on the 5th edition of the textbook. It's okay to have a different edition. Some people have the 4th, some people get the 6th. It's all perfectly okay. And even though the numbers of the problems aren't exactly the same, if you just follow the numbering on the syllabus, you'll still get a reasonable sample of problems that cover the material. So any version of the book is okay. I assume also that you're all signed up for Math 155, which is the calculus laboratory that goes with the course. And that's a very valuable thing, but it's a separate course with a different instructor and a separate grading system. Okay. Oops, people are still coming in. So right now, the way Zoom is set up, there's an obligatory security system, which means that when you log on to Zoom, you go into a waiting room and I have to admit you. So that's one of the reasons for this little delay at the moment. Okay, so let me start. Now, if you have a question, feel free to unmute yourself and ask the question. Also, let me know. I have on my screen the whole screen taken up with this piece of paper in front of me. So I hope everyone can see it without any difficulty. Right? You can ask questions either by unmuting yourself and asking a question, or going to chat and typing in the question on chat, and I will check chat periodically to see if there are any questions. Okay. If not, then we are ready to start. Good. So section 1.1 is on the graph of an equation. And the simplest equations, which we spend a lot of time with in calculus, are linear equations, things of the form y equals ax plus b. So a simple example would be, let's say, y equals 2x plus 3. And a simple way to plot anything, or at least to start, is you can always kind of make a table. So for different values of x, what is the corresponding value of y? So if x is 0, this is 2 times 0 plus 3. If x is 1, this is 2 plus 3, which is 5. If x is 2, you get 4 plus 3, which is 7. If x were minus 1, this would be minus 2 plus 3. 3 minus 2 is 1. If this were minus 2, this would be minus 4 plus 3. 3 minus 4 is minus 1. And let's just plot these points and see what they look like. So when x is 0, y is 3. When x is 1, y is 5. When x is 2, y is 7. When x is minus 1, y is 1. When x is minus 2, y is minus 1. So those are these points, and it looks like they lie on a straight line. Now, in fact, they do lie on a straight line. The fact that these 5 points look like a line on a straight line is kind of irrelevant. It's just like we were lucky, perhaps, because this really is a straight line. But in the simplest way that you learn how to graph things, you choose a bunch of points, a finite number of points, you compute the x and y values, and you draw what you hope is the graph. It's only a hope, and yeah, it's only a hope. So one of the things we will learn in calculus is how to actually have techniques to let us draw much better graphs. That's the whole point. Let's take another example. Suppose we take y equals x squared minus 2. So let's look at some values of x and y, maybe 0, 1, 2, and 3. So when x is 0, you get minus 2. When x is 1, you get minus 1. When x is 2, you get 4 minus 2 is 2. When x is 3, you get 9 minus 2 is 7. When x is 4, you get 16 minus 2, which is 14. Let's see what happens if we just plot these points. So 1, 2, 3, 4. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So when x is 0, it's negative 2. When x is 1, it's negative 1. When x is 2, it's 2. When x is 3, it's 7. When x is 4, it's 14. So this is what we get, something that looks like that. And what does that tell you about the graph? Well, truthfully, it doesn't tell you very much. I mean, could be going up forever and down forever, and who knows, all right? So if we just pick these 5 points and compute these numbers, we get information, but it's not really enough to understand the graph. Let's see, let's look at some negative values. Minus 1, minus 2, minus 3, minus 4. When x is minus 1, 1 minus 2 is minus 1. When x is minus 2, 4 minus 2 is 2. When x is negative 3, 9 minus 2 is 7. When x is negative 4, 16 minus 2 is 14. So if we plug in those values at minus 1, it's minus 1. At minus 2, it's 2. At minus 3, 7. And at minus 4, 14. And now, if you were to sketch in this graph, on the left, on the right, we would have sketched something like this, and it's not clear at all what would happen, but when we have these points on the right, So now you see you have something which looks like a parabola. But it's really very interesting because if you only had taken, let's say, the points from 0 to 4, you wouldn't have known it was turning around and going up. And if you only had taken the points from -1 to -4, it looks like something which is always going down. So it's very useful to get some idea of what the shape of the graph of a function looks like by calculating some points. But you have to keep in mind that it gives you some information, but not total information, and it can be misleading. Right? It's always a very good thing to compute some points, but you have to be a little bit careful about how you understand the points. Right? Are there any questions about that? One of the things you will learn in Math 155, using whatever program your instructor uses, hopefully it's Maple, some people use something called GeoGebra, you will learn how to have the computer graph a function for you, and you get a perfect, basically a perfect graph of the function. It's quite an extraordinary thing that in Maple, for example, simply using the command plot, you can plot the graph of any function you like, and all the guesswork is gone. Of course, the guesswork is gone because people have spent a lot of time understanding how to graph functions and writing the software to implement their understanding. When you have a graph, there are certain points that are interesting. So suppose this is the graph of a function. This is the x-axis. This is the y-axis. And here we have the graph of the function y equals f of x. And this graph crosses the x-axis at certain points. It crosses the x-axis here, and here, and here, and here. So these are called the x-intercepts. So the x-intercepts are the values of x where when you plug in y equals f of x, you get 0. So here, 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 and here, these are y-intercepts. So at these points, x1, x2, x3, x4, those are y-intercepts of the function. And there can be 1 or 2 or infinitely many or 0. So for example, if you take the function f of x equal to sine of x, the graph of this function is oscillating like this. There are infinitely many x-intercepts. And we know that f of x, which is sine of x, equals 0, if and only if this symbol, which mathematicians like to write, a double-headed arrow, is read if and only if and only if x is a multiple of pi, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so forth. Any integer multiple of pi, positive or negative. So this function has infinitely many x-intercepts. If you take the function f of x equal x squared plus 1, that's a parabola you know and love. It looks like this. It's the normal parabola y equal x squared moved up by 1. And this function has, so this parabola has no x-intercept. So functions can have a finite number of x-intercepts, an infinite number, or zero. All of those things are possible. Any questions so far? We also have, if this is a function, what is called the y-intercept. So a y-intercept is where the function crosses the y-axis. Here's the y-axis, and a function, well, if it crosses the y-axis, it crosses it at most one point. So you can never have more than, well, for a function that's y equals f of x, you can never have more than one y-intercept. But a y-intercept is a it's the value of, so it's easier to say it like this. A y-intercept is a point where the graph crosses the y-axis. So for example, when we had the parabola y equals x squared plus 1, the y-intercept is y equals 1. That's where this graph crosses the y-axis. Now, we can look at graphs of functions or graphs more generally. Suppose we had the equation, let's see, instead of y equals x squared plus 1, suppose it's x equals y squared plus 1. And the graph is all points x, y that satisfy the equation. Let me make it slightly different. Suppose it's y equals x squared minus 4. So what are all the points in the plane that satisfy this equation? So for example, if y is equal to 0, x would be minus 4. Let's make a graph like this, say different values of x and y, but let's say now that y equals 0, x is minus 4. If y is 1, x is minus 3. And if y is minus 1, y squared is still 1. So this is actually plus or minus 1, minus 3. So here and here. When y is 2, I get 0. And when y is minus 2, I also get 0. So plus or minus 2. When y is 3, y squared is 9. 9 minus 4 is 5. I'm out here. And the graph of this, it's a parabola, which instead of going up, is going to the right. And in this case, I have two places where the graph crosses the y-axis. I have this point, and I have this point. This point has coordinates 0, 2. This has coordinates 0, minus 2. So this graph has two y-intercepts, 2 and minus 2. So if you have some function of x and y, for example, some polynomial of x and y, it's like this, and you get all the points in the plane that satisfy that equation, that's what is called the graph of the equation. And you can have more than one y-intercept. Are there any questions about this? Okay. Symmetry of a graph. Fortunately, you have a book where everything is printed neatly, so the problem that I write poorly is not such a bad thing. Symmetry of a graph. So if you have a graph like this graph is said to be symmetric with respect to the y-axis. So geometrically, you can think of it like this. Imagine that you took this graph and you rotated it around the y-axis. You'd end up with the same graph. That's what it means to be symmetric around the y-axis. A rotation around the y-axis produces the same graph. What happens to a point if you rotate it around the y-axis? If this is the point x, y, so this is x and this is y, when you rotate it, you get to the point over here. This is minus x, but the same value of y. So algebraically, we can say a graph is symmetric with respect to the y-axis if whenever x, y is on the graph, it implies that the point minus x, y is also on the graph. So symmetry with respect to the y-axis means if you reflect around the y-axis, the graph doesn't change. You can also have a graph that looks like this. Now with this graph, if you reflect it around the y-axis, it's completely different. It looks just completely different. But if you reflect it around the x-axis, it doesn't change. What does it mean to take a point and reflect it around the x-axis? Well, if this is the point x, y, when you reflect it around the x-axis, it's the same value of x, but the negative value of y, x minus y. So we say a graph is symmetric with respect to the x-axis if x, y on the graph implies that x minus y is on the graph. Okay. So in terms of symmetry, here are two kinds of symmetry. Symmetry with respect to the x-axis, and symmetry with respect to, symmetry with respect to the y-axis, and symmetry with respect to the x-axis. And there's a third kind of symmetry that we will talk about in this course, which is a graph symmetric with respect to the origin. That's the point 0, 0. So for example, if you have a graph that looks like this, goes up, turns around, comes down, turns around, and goes up again. Now, this is not symmetric with respect to the y-axis, because if you flip it around, instead of going up on the right, it's going up on the left. And it's not symmetric with respect to the x-axis, again, because instead of going up as you move to the right, it would be going down as you move to the right. But it is symmetric with respect to the origin. That means that if you take a point x, y on the graph, and you draw the line from that point to the origin and continue it, it hits the graph again at the point minus x minus y. Okay? That's what symmetry with respect to the origin means. If you somehow reflect through the origin, so you take every point x, y, and you send it to the point minus x minus y, you're back on the graph. So the graph is symmetric with respect to the origin if x, y on the graph implies minus x minus y is also on the graph. Let's see, so I see a couple of messages on chat. I don't need to take your name for attendance. Actually, what I'm going to use for attendance is just turning in the homeworks. So I don't take attendance as part of your grade. I do have to record within about 2 or 3 weeks after the start of the term if someone has never showed up. But the only way I have to do that is by seeing who hasn't turned in any homework. So if you haven't turned in any homeworks, I assume you're not registered for the course, and I report that. Okay. Okay. There's one more point that the text is making in this first section 1.1, which is points of intersection. So a point of intersection of the graphs of two equations is a point xy that satisfies both equations. That means it's a point that lies on the graphs of both of the equations. So the text gives a pretty example. By the way, I always try as much as possible to use examples that are in the textbook. And that way, when you're studying at home or reviewing the lectures, you can actually see very clearly what's going on and everything is labeled properly and done legibly. So suppose we have the graphs of, in fact, in this section, this is example 5. We have x squared minus y equals 3 and x minus y equals 1. So we look at all the points that satisfy both of these equations. What is this equation? We could write this as y, rewrite this as y equals x squared minus 3. Then we know this is a parabola where the y-intercept is -3. When x is plus or minus 1, it's -2. When x is plus or minus 2, it's plus 1. When x is plus or minus 3, 9 minus 3 is 6. So this equation has a graph which looks like this. That parabola. And x minus y equal 1, I could rewrite that as y equals x minus 1. So this is a straight line. The y-intercept is -1, and it goes up with slope 1. So this line looks like this. So this is the line. And it crosses the parabola in 2 points. This point is the point 2, 1, and this point is the point -1, -2. And you can check. When x is -1, y is -2. When x is 2, y is 1. Here, when x is 2, y is 1. When x is -1, y is -2. So these 2 points lie on the line and on the parabola. So these points lie in the intersection of these 2 graphs. That's what we mean by a point of intersection. Any questions so far? You can either unmute and ask me, or you can ask on chat. Okay. Section 1.2 is called linear models and rates of change. And this is, again, just a review of what you spent a lot of time in high school learning about, which is namely straight lines. So if you have a straight line and you take 2 points on the line, x1, y1, and x2, y2, the slope of the line is how far up you move divided by how far you move to the right. It's the change in vertical distance divided by horizontal distance. So as you go from x1 to x2, this distance is x2 minus x1. And as you go from y1 to y2, the height, this difference is y2 minus y1. And what is called the slope of the line is, so sometimes people like to call this delta x. This is the capital Greek letter delta. And this delta y, the slope of the line, is the change in y divided by the change in x, or y2 minus y1 over x2 minus x1. So the slope of the line passing through these 2 points is this. Now, the miraculous fact is, if you take the equation, let's say y equals mx plus b, and we look at all the points that satisfy this, the graph of such a thing is what we call a straight line. You get the same slope no matter what 2 points you pick. So for example, if we have y2 is mx2 plus b and y1 is mx1 plus b, when we compute y2 minus y1 over x2 minus x1, this is my denominator. Y2 is this, mx2 plus b, and y1 is this, mx1 plus b. What do we get in the numerator? The b's cancel. We get m x2 minus x1 over x2 minus x1. These cancel. We get m. So if you take a straight line, or you take the equation y equal mx plus b, if you take any points x1 and x2 and calculate the y1s and y2 that correspond to them, the slope doesn't depend on the points you choose. It's always equal to m. That's why we call this number m in this equation the slope of the line. So what's very important is, and notice in this case, m equals the slope. If you let x equal 0, y is equal to b. So b is the y-intercept. So whenever you have the equation y equals mx plus b, the graph of the equation always looks like this, could be going up or down. The y-intercept is b, and the slope is m. Okay. So y equal mx plus b is called the slope intercept form of the line. Right? M is the slope, b is the y-intercept. But sometimes we want to have a different form of the equation for the line, what is called the point slope form of the line. See, in this case, so we were given the slope equal m, y-intercept equals b. In this case, we're given a point, x1, y1 lies on the line. and m is the slope. So what we're told is we have a point, x1, y1, lying on the line, and we want the line through this point with slope m. So we can actually work out the formula for this. Suppose we take xy. If xy is any point on the line, then the slope m is y1 minus y over x1 minus x. That's equal to m. So if we solve this equation for y, we get y1 minus y is, actually, this is correct, but let me just write it slightly differently and save a little bit of work. I can also write this as y minus y1 over x minus x1 is equal to m. So y minus y1 is m times x minus x1, or y is equal to m times x minus x1 plus y1. So this is the point slope form of the line. Okay, so far? This is really very important. This we use all the time. Okay. So for example, let's see if there's an example in the book I can follow. Find the equation of the line through the point 1 minus 2 with slope 3. So how do we do this? The slope m is 3, so y is equal to 3. X minus x1 is 1, plus y1 minus 2. So this is 3x minus 3 minus 2, or y equals 3x minus 5. Okay. So this is using the point slope formula to find the equation of the line through the point 1, negative 2 with slope 3. And you notice when x is 1, y is negative 2. So this works out fine. Okay. Section 1.3 is on functions and their graphs. So you can think of a function as a kind of what is called in science a black box. Here you have some function, f, and you plug in a number x, and what comes out is a number y, which we call f of x. That's what a function is. And sometimes functions has simple forms like f of x equals 3x minus 5, the line we just saw. You plug in x and you get out y, which is 3x minus 5. Sometimes it's much more complicated. But the important fact about a function is that for every x, there's a unique y which the function calculates. This x is called the independent variable. And y is called the dependent variable, because y depends on x. Now, what are the values of x? So here's an example. Suppose we take the function f of x equal the square root of x. So you can't take any value of x and calculate this, because we're just working with real numbers, and there's no square root of a negative number. So this is only defined for x greater than or equal to 0, not for all x. And in general, what is called the domain of a function f is the set of values of x for which we compute the function, for which we can calculate the function. I'll make it easy, for which f of x is defined. And the range of a function x, a function f, is the set of all values f of y, f of x, for all x in the domain. This means all the values of f of x that can come up. There's a more precise definition, which we really don't need, which is the following. A function with domain some set x and range some set y, we can think of it like this. For all x in the set x, you can plug it into the function, and out comes y, and y is in this set capital Y. So for us in calculus, this is not really too important. The most important thing is to understand that functions are simple functions like the square root of x are not defined for all x necessarily. And so you have to understand, you have to be able to calculate what is the domain of the function, for what values of x the function makes sense. And so for a function like f of x equal the square root of x, this only makes sense for x greater than or equal to 0. Let me just give a few more examples, which in calculus turn out to be significant. So f of x equal the square root of x. So this is the function. What is the domain? Well, it's defined for x greater than or equal to 0. Suppose we take f of x equal the square root of x minus 1. So this is defined whenever x minus 1 is greater than or equal to 0, or x greater than or equal to 1. Suppose f of x is the function x squared minus x squared plus 3. Sorry. Make it x plus 3. So this is defined whenever x plus 3 is greater than or equal to 0, or x greater than or equal to negative 3. What about f of x equal to the square root of x squared plus 3? Well, this is defined whenever x squared plus 3 is greater than or equal to 0, but this is all x, because x squared is always non-negative. So all x, or we could say all x from minus infinity to plus infinity. Suppose f of x is x over x plus 2. Well, here there's no question about issues with square roots, but you know you can't divide by 0. So the domain is wherever the denominator is not 0. X plus 2 not 0, or x different from -2. Or we could write that as all x less than -2 minus infinity, and x greater than -2. Suppose f of x is equal to x squared over x squared minus 9. Well, again, the numerator doesn't matter to us, but we just have to worry about the denominator not being different from 0, not being equal to 0. So the domain is all x, where x squared minus 9 is not 0, which means x not equal to 3 or -3. So on the number line, we could draw it like this. -3 is not in there, but everything from -3, from minus infinity up to -3, everything in here, and everything out here. So it's all real numbers except these two numbers, 3 and -3. Okay. That's the domain of the function. Okay. There are other nice things you can do to functions, just ways to move them geometrically. So these are transformations of functions. So suppose we take a simple function, y equal x squared. That's the parabola you know and love. You can perform a vertical shift upwards or downwards. So from y equal x squared, I can move it up, let's say 2 units, and y equals x squared plus 2. So from this parabola, I moved it up to that. That's a vertical shift. You can have a horizontal shift. So here's this parabola. And let's say I shift it 2 units to the right. So I move it over. So I end up with parabola that looks like this. So the equation of this red parabola is y equals x minus 2 squared. When I shift something by x by a certain number of units, like 2, I replace x by x minus 2. And you notice this is a parabola. It's a quadratic polynomial. When is it equal to 0? When x equals 2. So for this parabola, the vertex is at 2, and then it's going up. You can also have a reflection. So what's a reflection, for example, around the x-axis look like? Here's the parabola going up, when I reflect it around the x-axis, it looks like that. And so from the parabola y equal x squared, when you reflect it, it's y equals minus x squared. Right? The point xy goes to the point x minus y. That's reflection around the x-axis. So if you write these things in terms of functions, if you have a function y equals f of x, a vertical shift by some amount like 2 would be, you would get the function y equals f of x plus 2. When you have a horizontal shift, for example, by 2, y equals f of x would go to y equals f of x minus 2. When you have a reflection around the x-axis, y equals f of x would go to y equals minus f of x. And a reflection around this is a reflection around the x-axis. When you reflect around the y-axis, you would just replace x by minus x, and so on. Okay. Let me explain one more final transformation, which is composition of functions. So suppose we have two functions, f and g. I just want to picture it as a black box for the moment. So let's say you put x into this function f, and out comes some number, let me just call it for the moment u, which is f of x. But I take this number and I plug it into the function g. And if you put u into g, what comes out is g of u, which I'll call y. So you start with x, you apply f to it, you get some number u equal f of x, and then you plug that into the function g, and out comes another number. So you start with an x and you end with a y. And so we call this composition of functions. We write this as, so this number that you end up with, y, how did you get it? You started with x, you computed f of x, and then you took g of f of x, and that's what we call y. And we also write this as the function g composed with f, sometimes write a little circle there, of x. This is composition of functions. And this is really extremely important because most functions in calculus arise as compositions of much simpler functions. So what's an example? Let's look at some examples that are in the text so you can follow this at home yourself if you like. So suppose we have the function f of x equals 2x minus 3, and we have the function g of x equals the cosine of x. So what is g composed with f of x? This means g of f of x. What is f of x? F of x is 2x minus 3. So this is g of 2x minus 3. What is g of anything? It's the cosine. So this is the cosine of 2x minus 3. So that is the composite function g composed with f. So given any two functions, you can compose them. what happens if I compose them in the opposite order? F composed with g of x. This is f of g of x. G of x is the cosine, so this is f of the cosine of x. What is f of the cosine of x? It's 2 times the cosine of x minus 3. And you'll notice these are 2 completely different functions, right? Completely different functions. So g composed with f is not equal to f composed with g. You know, when you're multiplying numbers, 2 times 3 is 6 and 3 times 2 is 6. It doesn't matter what order you multiply them in. But when you do composition of functions, the order really does matter. Okay. All right, so while you are mulling over this, I think I actually will take attendance just because it's convenient to know who was here the first day. So I will call your name as I write it down, and if I miss you, then you'll send me a message on the chat to say that I missed you. So I have Osman, Scott, Atkins,
I'm here, Professor.
just a second. Atkins.
I'm here.
Oh, no, I'm not asking if you're here. I'm taking down the names that I see on the screen.
Oh,
Rez, Goulon, Noble, there's an Isabella M, but I don't know what the M stands for. Said, Gonzalez, Eric Aqua, Seymour, Thomas, German, Calderon, Garcia, Sizavani, Reyes, Guan, no, I think I missed somebody. So is there anyone whose name I didn't just call? Let's see.
I don't know if you called mine. My name is Austin Perez. I didn't hear you take
Yeah,
that.
no. Perez, I got you.
Okay.
Perez, Said, Reyes, Thomas, Calderon, German, Atkins, Akua, Isabella M, Gonzalez, Yuan, Osman, Noble, Garcia, Scott, Goulon, Seymour, Khan. I missed a Khan. Khan, Sizalana. Yeah, that's okay. Good. All right, I got everybody. Good. Okay, that's composition of functions. What other topics are part of this pre-calculus review? Well, the exponential and logarithm functions. So this is section 1.6. So exponential functions look like this. You have simple things like y equals 2 to the x or y equals 10 to the x. But the most important one is y equals e to the x, where e is one of the most important numbers in calculus. The most important numbers in calculus after 0 and 1 are pi and e. And e is approximately 2.718. And exponential functions grow like this. And they have inverses. So this is exponential functions. That's the most important one, but there are plenty of others. And then we have the logarithms. So you have the log to some base, whatever it might be. And the most important logarithm function is the log to base e. So this is the log to base b, but the log to base e, the book writes as ln of x. So this is what is called sometimes the natural logarithm. And it's expected that you know, you've learned at some point, some of the basic properties of the exponential and the logarithm functions. So if you have the exponential function, if you take e to the sum of two powers, that's e to the x times e to the y. That's the most important property. E to the 0 is 1. E to the x minus y is e to the x divided by e to the y. And for the logarithm, the log of the product is the log of x plus the log of y. And the log of 1 is 0. The log of x divided by y is log x minus log y. And the log of x to a power is a times the log of x. So this is supposed to be review. And I'm putting these down just so you see them, because we're going to use them over and over and over again. But it really is important for you to review the properties of the exponential and logarithmic functions. For the domain of e to the x is all x. The exponential function is defined for all x. The logarithm is different. The domain of the log of x is just positive values of x, x greater than 0. This is the logarithm. It's only defined for positive values of x. If you wanted to find for negative values of x, you could look at the function log of the absolute value of x. That's defined for positive and negative values, but it's not defined for 0. All right, there's one last bit of review, which is some trigonometry. So this is Appendix C in the 5th edition of the book. So C.3. So this is Appendix C.3, trigonometry. So if you want to measure an angle, theta, the important thing is to know that once you're out of high school, you never measure angles with degrees. So to say that a right angle is 90 degrees is true, but doesn't work for us. We don't measure angles in degrees. You measure angles in radians. And what is radian measure? So here's an angle theta. And how do we measure it? Well, you draw a circle. So draw this angle. So the vertex of the angle is at the origin in the xy plane. And you draw a circle of radius r. And this angle cuts out a certain amount of the circumference of the circle. So call that S. So S is this arc length. And the radian measure of theta is the length of the arc of a circle it cuts out divided by the radius of the circle. That's the radian measure. Now, what do we know about arc length? We know that the circumference of a circle of radius r is 2 pi r. So this arc length can be anything from 0 to 2 pi r. So S divided by r is between 0 and 2 pi. So the radian measure of a circle is between 0 and 2 pi. Suppose we take, for example, a right angle. That's a right angle. Draw the circle of radius r. What is the length of arc that this right angle cuts out? Well, S is 1/4 of the whole circumference. The whole circumference is 2 pi r. So this is 2 pi r over 4. 1/4 of the circumference. So S over r is 2 pi over 4, or pi over 2 radians. So a right angle is pi over 2 radians. What is the length of what in high school you would call a 45-degree angle? Well, Here's a 45-degree angle. If you draw a circle, it's 1/8. This arc that it cuts out is 1/8 of the circumference. So S is 2 pi r over 8, or pi r over 4. So S over r is pi over 4 radians. So pi over 4 radians is what you used to call 45 degrees. Suppose we take an angle which in high school you would call 30 degrees. Well, this angle, this arc that it cuts out is 1/3 of this, which means it's 1/12 of the whole thing. So this S is the circumference divided by 12. 2 pi r over 12, pi r over 6. So S over r is pi over 6 radians. So pi over 6 radians is 30 degrees. If you went all the way around, 2 pi radians is equal to 360 degrees. So if you actually want a formula to convert degrees to radians, 1 degree is equal to 2 pi over 360, or pi over 180 radians. So that's the formula to convert from degrees to radians. Yep. That's what it is. And the last thing you have to review, and it's in whatever edition of the book you have, there's always some review of trigonometry, are the trig functions. So if you have an angle theta, what is the sine of theta? Well, if you draw a right triangle with theta as one of the angles, let's say theta is between 0 and 90, the sine of theta is, so for this angle, this is, in this right triangle, this is the hypotenuse. This is the adjacent side, and this is the opposite side. Sine theta is opposite over hypotenuse. If I call this x and this y and this r, it's y over r. Cosine theta is adjacent over hypotenuse, which is x over r. Tangent theta is opposite over adjacent, which is y over x. The cotangent of theta is adjacent over opposite, x over y. The secant of theta, so the cotangent of theta is 1 over the tangent of theta. The secant of theta is hypotenuse over adjacent, r over x, which you'll notice is 1 over the cosine. And the cosecant of theta is hypotenuse over opposite, r over y, which is exactly the reciprocal of the sine. So you need to review the trig functions, and you must know the values at the basic angles, which are pi over 4, pi over 6, pi over 3 radians, 0, pi over 2, pi. These are really basic things. And you have to, in order to do this, you have to remember, you have to know the basic principle of what's called a 30, 60, 90 right triangle. If this is 30 degrees is pi over 6 radians. If this is, then this is pi over 3 radians. This is pi over 2. If you take the hypotenuse to be 1, this is a right triangle, this triangle drawn in the unit circle. This is a half, and this is root 3 over 2. And the other right triangle, which you have to know, is when you have an angle of pi over 4 radians, or 45 degrees. If this is 1, this is 1 over root 2, and this is 1 over root 2. So these triangles you have to know. Okay, Isabella, I got your last name. Thank you. All right, so we did a lot today, but it's supposed to be review, but these things are really, really important. So starting next week, I have office hours, Mondays and Wednesdays, certainly from beginning of 1 o'clock. And you're always welcome to, it's on a Zoom session, and the Zoom login is on the website, and I also emailed it to everybody. It's on the instructions for the course. And you're welcome to Zoom log into any one of the office hours and ask questions about anything. So I'm happy to answer questions about material that's part of pre-calculus, but in the regular lectures, I'm not going to be going over it because this is all what you're supposed to know in principle. Some people know parts of it, and no one knows all of it usually, but I have office hours, and I'm happy to answer questions about any of this. All right, so that's a lot for the first day of class, and I think I'm going to stop at this point. I also covered everything in lesson 1, I believe. So calculus proper starts on Monday, and a large part of calculus, or what's called mathematical analysis, has to do with the notion of a limit of a sequence of numbers, and that's what we'll talk about. Are there any questions before we end? You can either unmute and ask me, or you can
Yeah,
a question on
just
chat.
I wanna confirm just 2 or 3 things. So all the information that you just talked about now, is it in the textbook that you the recommended textbook?
Well, it's the required textbook, but yes.
Okay. Is any of this information going to be posted on Blackboard, or is everything just going to be straight uploaded to YouTube?
So this lecture is being recorded, and I will upload it to YouTube. It's much easier to access. From past experience in the spring and then in the summer, in the spring semester when we went online, I posted everything on Blackboard, and a lot of students had trouble getting it or finding it. Blackboard was much harder to navigate. In the summer, I used a YouTube channel, and there was no problem at all. I mean, YouTube is much better from this point of view. So, so the lectures will be on YouTube, and they're really easy to get. So there's no reason to post it on Blackboard also. What I will be, I've already posted on Blackboard information about the course. I've posted the syllabus, which is the departmental syllabus, and I've posted the class and homework schedule for the whole semester. Let me say, with homeworks, you do homework and you upload it to Blackboard. The way you upload it is you take your homework, and my experience is most people, not necessarily everyone, but most people have access to a printer. You don't have to print it, but most printers now, I mean, almost every printer that I've seen, will allow you to scan a document. So you scan your homework and you get one PDF file and you upload the PDF file to the assignment section of Blackboard. So for example, next Wednesday, homework 1 is due. So you'll do the homework on, pieces of paper, scan it, and you should set the scanning so you get one PDF document with multiple pages, but it's one PDF document. You go to Blackboard, you go to assignments, you'll see homework 1, you'll click on it, and it will allow you to upload the homework. And you will get a grade for the homework, because the homework counts. And all the grades for homeworks and exams are available to you instantly in the grading part of Blackboard. So we use Blackboard, but we just don't use it for everything. We use Blackboard for everything except for storing the videotapes of the lectures.
And somebody said in the chat, is the homework the same questions and like editions 4 and 6?
It doesn't matter.
Or-
So what I said
okay.
was, so the important thing is that you do problems. Most of the time they're the same. Sometimes they've renumbered or changed a problem or two. But the point of the homework is to have practice doing calculus. I don't grade individual problems at all. What I want to see is that you're doing the homework. So if you've done a reasonable, if you don't turn in the homework, that's 0. If you turn in, a significant amount of work for the homework, you get the full 2 points. If you do just 1 or 2 questions and that's it, you'll get 1 instead of 2 points. So I just look at how much you've done on the homework. If you have a question about a problem, you're always free to ask me either in one of my office hours, or typically at the beginning of every class, like, every 9 o'clock class, I will ask if there are any questions. And if you have a question about a problem, I will do it and everyone will see how to do it as well. Let's see. Zahra Khan, I have your name in the attendance, no problem.
Can you show the book one more time, please?
Sure. So the 5th edition is this. Like most calculus books, it is tremendously overpriced. It's obscenely expensive. So I encourage you not to buy a new edition, if at all possible, to try and get a used copy somewhere. And that's why it doesn't really matter too much which edition you get. I'd rather you not have to spend $200 for a book. I mean, the book is used for all 3 semesters of calculus at Lehman. So, if you buy it once, you can use it for Calc 1, Calc 2, and intermediate calculus if you take the whole calculus sequence. But every calculus book I know is overpriced. This is the one the department chose for whatever reason. Okay. If there are no more questions, let me look at chat. I don't see anything new on chat. So,
Professor,
yeah,
I have the book for the edition 4. Is it gonna work for the homework question?
it'll be close enough. The important thing is to do problems. The only difference between editions 4, 5, and 6 in the homework is they might add or subtract 1 or 2 problems. They might change a number, but it still covers the same material. So if you have edition 4, there's no reason to go out and buy a different edition. You will learn all the material studying the book, edition 4, 5, or 6.
Okay, thank you.
All the homework is in the book. Just check the syllabus. Okay, everyone have a good weekend, and I will be back here. Hopefully we'll all be back here on Monday morning. Bye.
You have a good day.